Okay, into 1. This is what you get. So I was basically sub Q 2 into 1. This is Q, right? This is Q, right? Okay, I'm going to sub it here. Okay, I'm going to sub it here. Alright, this is what I get. I have 2p minus p squared plus 8 plus 2i multiplied by I equals to 2. Follow me? Follow me so far, huh? Okay, I don't check. Okay, don't look at boys, don't look at girls. Okay, look at me. Okay, so very quickly, right? What I'm going to do is I'm going to force this into a quadratic equation. Okay, I'm going to arrange this such that I'm going to get a quadratic equation where my variable is p. Where my variable is p. Okay, so quickly you have ip squared minus. Okay, this is after you're simplifying. Okay, so you simplify. You have 2p minus ip squared minus 8i minus 2i squared equals to 2. 2i squared is just equals to negative 2. Very good. Okay, so I just simplify this. So this becomes positive 2. Okay? Alright, cancel off. This is what you get. Okay? Then very quickly, you have a negative ip squared minus 2p minus 8i. Sorry, plus 2p minus 8i. Converting this, I would like my coefficient of p squared to be positive. ip squared minus 2p plus 8i equals to 0. This is all we have. This is the quadratic equation in terms of p. So your quadratic formula that you learned in the past, remember ax squared plus bx plus c, the favorite secondary tree E math. Okay, so you have this x equals to negative b plus minus square root b squared minus 4ac over 2a. That's precisely what we're doing here. We're using that to help us solve the quadratic equation. Okay, so here I recognize that, okay, a is I, b is negative 2, c is 8i. With that, I happily and sincerely just use my quadratic formula. Okay, so p equals to negative b, so negative of negative 2, right? Plus minus b squared, so I get 4, minus 2ac, so minus 4ac, minus 4ac, which is 8i, over 2a, so it's 2i. Alright, so I will leave you to simplify this. So basically, okay, I'll say again, you forget everything I say. This is the gist, right? We are using quadratic formula. There are many ways to solve this. This is just one of the ways. Okay? And all goes well. Simplifying your answers here, you should have p equals to negative 4i or p equals to 2i. Okay, I see you copying, so I'll pause a while, let you copy, because I'm going to go to the next page, okay? Very good, you're so well behaved today. Okay, that's not all. I found p. Okay, so what do I need to find next? I found p in simultaneous equation. We find x, we need to find y. Okay, so we find p, we need to find q. Okay, this is my p. Next page, ready? 3, 2, 1. Okay, so if p equals to negative 4i, similarly you can find, right, your q will be equals to negative 8 plus 2i. P equals to 2i, alright, similarly you can find q to be equals to 4 plus 2i, alright. So I'm not going to show you the nitty-gritty details of substituting p equals 2i into your equation. Alright, I'm sure you can get it. Okay, so I just need to verify. Okay, once your pen stop moving, you look at me and start to look bored, then I will move on. Okay, fine. Okay, children, can I go on? Okay. Ready? Yeah? Okay. Okay, I'm going on. Okay, I'm moving on. Next one. Okay, so this is how it looks like. Okay. Just a recap again. Okay, if we were to do x squared, x and c, your quadratic formula, your coefficients need not be real. Okay, doesn't mean that, what we learned in Sec 3 doesn't apply here. quadratic formula still can be used. Alright? So remember we did this. Right? The variable is p squared and p. This is a quadratic equation. Your variable is p. Right? Okay. Question 6. Square root of complex number. How do we solve a typical question where, okay, I know this in your lecture question, so I'm just going to go through with you, alright, very quickly. We are required to evaluate square root 3 minus 4i. There's no plus minus, remember, there's only a square root. Positive square root of 3 minus 4i. How do we go about doing this? Are we able to find a square root? Maybe we cannot. So what we do is we work backwards. Okay? Using the understanding last time around, we say, there's this equality of complex number, right? There's this equality of complex number. So we always use the understanding of the equality. Okay? Equality of complex number, remember, we said, right, if x1 plus iy1 equals to x2 plus iy2, where all your x1, x2, y1, y2 are real, right? This just implies that x1 equals to x2, the real parts are equal, the imaginary parts are equal. This is what we did last time. Then after that, I'm going to use this idea to help me. Okay. If I let square root of 3 minus 4i to be x plus iy, okay? What I do next is we can square both sides. Okay, so from here, remember, this is the step before. Okay, all I do is I square both sides. Okay, I square both sides and then you can see, it doesn't matter. So now it looks as though 3 minus 4i, we can so-called start to compare the real and imaginary part. But before we do that, we expand this. Okay, so what I do here is I expand my complex number. Okay, x plus iy square is nothing but just it's like z square. It's just z square. Okay, it's just z square. Okay, so x plus iy square. Expanding this, remember x plus iy, you square it x plus iy. Right, you expand first in, last out. You're going to get the real portion to be x square minus y square. This is the real part. The imaginary portion, can you see, is here, right? So imaginary part is actually is equals to 2xy. Okay, the real part is equals to x square minus y square. All right. So again, children, all I'm doing is this. I'm going to compare the real parts. Where are my real? Okay, so look at my Apple Pencil. Okay, so I'm just look at the screen. Sorry, not looking at this. This one, this one. These are the real parts. Okay, so I compare x square minus y square equals to 3. Correct? Easy, right? Easy peasy, lemon squeezy. Okay, so after the next one, 2xy. 2xy. I compare with negative 4. Okay, so I have this. 2xy equals to negative 4. Okay, I get xy equals to negative 2, and quickly you can actually find your answers. Okay, that's how you get the rest of the steps. Okay? Can? This is for question 6. Alright, so if you deal with square root of a complex number, that's how you. So late, wow. Why so late? Okay. Can you come and see me later? Can you come and see me later? Yeah. Not going to scold you, just educate you. Okay. No, I never scold. Since I never scold before. Never scold. Always so nice. Okay. Yeah. Okay. I believe all children are good until proven otherwise. Okay. Then part 3. Okay. Next one. Next portion. Okay, we are going to find this chapter. This next part of the chapter, we're going to talk about conjugates. Okay, so conjugate, like we did last time, when did we first see conjugate? When remember, last week we were doing something like this, Z1 divided by Z2, correct? Then how do we do this? We actually use the so-called the conjugate example. If I have 2 plus 3i over 4 plus 2i, 4 plus 7i, correct? Then what we did is we multiply by 4 minus 7i, Okay, so this part, okay, we are called the conjugate of the denominator. Okay, this is what we did last week. Just a recap. How do we find the conjugate of a complex number? This is 1. And what are the properties of complex conjugates and their application? Okay, so these are 2 questions. I hope you can keep in your heart. We are going through this part, right? Let's go through it. Okay? How do we find the conjugate of a complex number? This is the definition. It's in your lecture question. So very simple definition. All you do is you take the real part, you go and multiply by negative 1. You just change the plus to minus to plus. Okay? So if you have x plus iy, the conjugate is defined as x minus iy. The conjugate is defined as x minus iy. Okay? So this is the conjugate. So with the conjugate, what can we do? Okay, there are a lot of fun things we can do. It helps us. This conjugate, the idea of the definition is it will help you to take a lot of shortcuts later on. Okay? So next one. Okay. Oh, okay. Properties. This is not in your lecture question, I believe. It is in your comprehensive notes. Okay, so what I need to do is okay, I'm going to let you look at this portion. Okay? Because it will help you with question 7 and question 8. Right? So Z and Z star. Okay, so in your some mathematics textbooks, okay, sometimes you all will see that your conjugate can also be written as Z bar. Okay, but in a Singapore context, we always write Z star. We don't write Z star or Z asterisk star. We don't use Z bar. We have to use Z bar. Okay. So these are the properties of your conjugate. It will help you later on. Okay, can Okay, so you will observe Z and Z asterisk. This is just x plus iy multiplied by x minus iy. Okay, we did this in question 2, so you realize actually, if I were to do the expansion, x and x minus iy, ixy, negative iy squared, this is what I have. Okay, negative iy squared, this will become negative of negative 1, right? So it becomes a positive of y squared, right? Positive of y squared. Iyx minus ixy, these two will cancel out. Okay, that's why when I multiply a complex number with its conjugate, I will get x squared plus y squared. Okay, so this is easy when you are doing division of complex numbers, for example. Okay, let me show you what I mean. Okay, sometime back, 1 week ago, before our terrific lecture test, right, we were doing this one. What were we doing? Okay. We were doing, I remember we were doing this, correct? So this is what we did last week. So this is actually a conjugate. And if you knew this rule at that point in time, you would have actually straight realized that Z1 and Z1 asterisk will just give you, right, x squared plus y squared. Okay? So this is convenient when you are doing division of complex numbers. Okay, so this property can help you. Okay? Okay, next one. Easy, right? X plus iy plus x minus iy. This is your z asterisk. This is your z. Okay, you can see these two will cancel off. So you just get 2x, which is 2 times the real part of z. Okay, and similarly the rest will follow. Here, the conjugate of the conjugate is just the original complex number, right? The conjugate of the conjugate, right? Z asterisk of z asterisk is just z itself. Okay? Yeah. Here, scalar, it doesn't affect. So kz asterisk is just kz. Okay? And hopefully you can see. Okay, this will actually revisit this later. Okay, so this one, I know if you look at this one, it looks a bit confusing. I'll actually show you this later. When we go into the exponential form of a complex number, we'll actually revisit this. Okay? Okay, so for now, let's just accept this first. Okay, so we'll revisit this later. You'll see why it works. You'll see why it works. Okay? Okay, now let me just give you about 5 minutes. Okay, maybe 10. Okay, I just need to try question 7, question 8. Okay? Question 7, question 8. Okay. As you try question 7, question 8, I will just purposely. Oh, I forgot to. Okay, so this is for question 7. How about, can I go on? Yes? No. Yes, no? I'm getting mixed responses. Yes or no? No, okay. No, stop here. Ready, Ready, okay. So part 4, right? With a complex number, we can form equations that involve complex number. The next thing we do when we have an equation, we think about how to solve it, right? So now, now with this equation that involves complex number, how do we find the roots? What do we know about the roots? Okay, or what kind of information can we derive from the roots? Alright, or what kind of predictions we can make based on the degree of a polynomial. Okay, so first one, what can we say about the roots of polynomial equation with real coefficient? Okay, this is one of the things with real coefficient. So remember, everything you do, first check that it's real. Yeah, it must be real. Okay. Then how do we solve polynomial equation with real coefficient? Okay, and understand that the complex roots with real coefficients occur in conjugate pairs. This is very important. Okay, this is very important. It occurs in conjugate pairs. Okay, so this is a prerequisite knowledge and then your lecture reading. Okay, fundamental theorem of algebra. Okay, every polynomial of degree n with coefficients, okay, in C has complex, okay, exactly n roots. Okay, your n roots need not be real, your n roots can be complex, okay, has exactly n roots, including repeated roots. What do I mean? Okay, so for example, secondary 1, secondary 2, we did a linear equation. X plus 2 equals to 3, x equals to 1. This equation, what's the degree? 1. Number of roots? 1. Okay, so after that, secondary 3 math, okay, then we did ax squared plus bx plus c equals to 0, right? So it could be that you have two real and distinct roots. It could be that you have two equal roots. Real roots. Sorry for my poor handwriting, I will work on it. Okay. Two distinct, or it could be equal unreal roots, or equal unreal roots. Okay? Cannot. But the idea is that there's always two, but it can be complex. This is what we did in secondary 3, right? So the main idea is this. Okay, what is the degree of this? Quadratic power 2, right? Degree 2, you have 2 roots. Degree 3, 3 roots. Degree n roots, right? But the n roots, right, need not be all real. Need not be all real or need not be all complex. Okay? However, fundamental theorem will tell you that if I have power 3, I'll have 3 roots. Need not be, we don't know how many are real, how many are complex. You will know soon. Okay? Next one, complex conjugate theorem. Okay, this will tell you that, listen, okay, all non-real roots of a polynomial with real coefficients, okay, they must occur in conjugate pairs. What does it mean? It means that, supposedly, children, today I give you, say, okay, ax squared plus bx plus c, okay? And let's say this is power 2, Let's say, okay, given that most importantly, a, b, c are real, okay? This is the most important. The polynomial, the coefficients must be real. Equality must be real. Polynomial coefficient must be real, okay? Must be really real, okay? Cannot be complex. Complex die already. You must go and change, okay? So it must be real. When it's real, your complex your roots occurs, let's say the complex roots, right, it occurs in conjugate pairs. Meaning, if I give you this, maybe this fx, okay, this polynomial, right? Okay, and I tell you that, oh gosh, 1 plus I is a root. It's a root, What does it mean? It means that 1 minus I is also a root. Okay, this is the general idea. It's also a root. Okay, but there are two conditions. Number 1, the coefficients A, B, C must be real. Number 2, then you can assume that, okay, the conjugate pairs. Okay, so I say again, they must be real, Then you can talk about the conjugate pairs. Okay, not real, no pairs. Okay, can Okay, so I'll stop here. Next Monday I'll explain this again. Okay, can. Okay, thank you for being so well behaved. See you all next week.